Okay, here we are on page 61, and this is the most important part. This is talking about the notation of end behavior, and you'll be using this for the rest of your life when you describe graphs. You do domain, range, increasing, decreasing, end behavior is something you will always add to your descriptions of graphs. So a little sketch will help you with this. So first thing you want to know, what is this graph? Well, this is a line with positive slope. So if I do a little sketch here, this is going to help me figure out what to do. In the end behavior, it says x goes to negative infinity. So as x goes to negative infinity, which is to the left, if x is going to the left, which way is y going? Y is going down, and the way we say down is negative infinity. It's going down to negative infinity. And as you plug in really big values for x, what happens to the y values? The y values go bigger, bigger, bigger. They are going to infinity. So if you plug in big X, the y's get bigger. As X goes to the right, Y is going up. Okay, now this one is what we call a quartic graph. It is a U-shape curve. So as X goes to negative infinity here, if you plug in negative, really big numbers, where is this graph going? It's going up. It's going up to positive infinity. And as you plug in really big numbers to the right, positive numbers, this graph is also going up. So this is kind of an up and up situation. If you plug in big numbers, you get positive numbers. And if you plug in negative big numbers, you get positive. Okay. 3 to the x is what we call an exponential growth function. It's not a polynomial. It is tripling each time. The graph will look like this. And as x gets really small, where is this graph going to? It's not going down forever. It's stopping. It's on its way to 0. It will never get to 0, but that's where it's trying to get to. And as you plug in really large numbers for x, this guy is getting very big, very fast, faster than any polynomial. This graph is a cubic. We would call it a snake baby from outer space. It would look like this. And as x goes to the left, as we go to the left and x is very small, this graph is going down to negative infinity. And as x goes to the right and gets really big, this graph is getting bigger as well and going up. Okay, this guy is also a cubic, but it has a major difference. This leading coefficient is negative, which flips this bad boy upside down. So now as x goes to negative infinity, this graph is going to positive infinity. And as x is going down to the right, it is going to negative infinity. Okay, now this is a logarithmic graph. And we talked about logarithmic curves. They look like this. And as x goes to negative infinity, we're going to say it's undefined. It cannot go to the left forever because you cannot plug in really numbers close to negative infinity at all. You could say as x goes to 0, f of x is going down to negative infinity, but we cannot say that it's going to negative infinity. But as x goes to the right towards positive infinity, it is also going up. Now this one is going very slow. This will be slower than any polynomial, but it is going towards infinity. Okay. These next graphs here, we're going to look at and say what the end behavior is by looking at the graphs. So this one is going down, and then here it's going up. So as you go to the left, as x goes to the left, what did we do? We went to negative infinity. We went down, and as we go to the right, it went up to positive infinity. Both of these on the ends, on down and down. So we're both going as x goes to negative infinity, it's going down. And as it's going to the right, to positive infinity, it's also going down. Okay, now, even and odd functions here. Okay, I'm not going to go through these differences with you. This is having you discuss it, and this is valuable when we're together. I'm just going to kind of tell you the difference between even and odd functions. Okay, so what you need to know is this. For even functions, if you have a function machine, if you plug in 2 and you get 5, if you plug in -2, you're also going to get 5. If you plug in 6 and you get, I don't know, 31, if you plug in -6, you're also going to get 31. Because when you graph these guys, they have y-axis symmetry. They have y-axis symmetries. Now, some kids think, oh, because the word even is there, everything with the x to the even number is going to be an even function. And that's only true if you move it up or down, like this or this. But if you move it left or right at all, if you move it left or right at all, it will not have y-axis symmetry anymore. Because if I plug in 7 here and -7, I'm not going to get opposites. Okay? So, y-axis symmetry for evens. And then, so the odd ideas mean these have 180 rotational symmetry, 180 degrees rotational symmetry. And what this means, this weird function stuff here, says if you have a function machine and I plug in 3 and I get 4, when I plug in -3, because I change the sign here, I have to change the sign here, I'm going to get -4. So if I plugged in 20 and I got -30, if I plug in -20, I'm now going to get +30. If you change the sign here, you change the sign there. That makes it flip-flop in the 180 rotational. That's what this notation means. If you plug in -x, you're going to get -y. Are all odd degree polynomials odd? No. Only if they go through the origin. And really only if there's a stretch factor. If you move it up, it no longer has 180 rotational. So if it has a stretch factor and it goes through here, it's fine, but you can't move it left to right or up or down. And are all functions odd or even? No, most are neither. Most are neither. We're going to hit even and odd functions more next year in Algebra 3. This is just an introduction to it. And that's all I need you to do for the notes. The homework tomorrow is actually relatively easy. There's a lot of factoring, and that will be on your test as well. But the end behavior idea, I think, is the most important thing here.